everyone. Thank you for taking the time to attend my presentation today. My name is Abigail Roberts. I am a December 2022 Carl Goodson Honors graduate, and today I will be presenting my thesis on the effects of red light intensity on the cultivation and oxygen production of Arthrospira platensis. My research with Dr. Taylor focused on an algae known as Arthrospira platensis, commonly known as spirulina. Between its nutritional benefits combined with its ability to absorb light and convert it to chemical energy, this algae possesses several characteristics that could potentially provide vital aid to space travel. For my basis of my research, I focused on light and specifically what intensity of light creates ample energy for spirulina to not only perform its job, but to do it cost efficiently. That is why I focused my study on lower red light intensities and compared them to previous results of spirulina grown under white light intensities to determine if the red light could be used as an alternative energy source to grow the spirulina while in space. When considering the physiological challenges that space travel creates, astronauts can encounter a variety of health threats during missions. These can include, but not limited to, bone density depletion, muscular atrophy, loss of body mass, impairment of immune function, and neurovestibular changes. Additionally, due to the increased exposure to radiation in space, the astronauts are also at a greater risk of developing cancer and degenerative diseases, including heart disease and cataracts. So rather than having to treat illness upon return, spirulina has the potential to act as a preventative measure throughout space travel. In addition to these physical challenges, there are also mechanical risks, including oxygen storage, viability of life-sustaining resources for long periods of time, and just the overall expenses of the trip itself. As you know, space travel is not cheap. And oxygen supply is obviously very important during long-term space missions. So when considering the physical and mechanical challenges, spirulina offers several solutions. Firstly, it is a food source that possesses significant nutritional value. Its high protein content combined with multiple vitamins and powerful antioxidant properties make spirulina great for immune support, which is important when on mission. It also can be easily cultivated with predictable growth, allowing for this food source to be grown in a compact space like a spaceship. The spirulina structure and genetic makeup plays a very large role in why it possesses these benefits. It is a planktonic filamentous cyanobacterium that is composed of individual cells, and it grows in subtropical alkaline lakes. It can survive under a wide range of conditions, but it thrives at temperatures around 35 degrees Celsius and a pH of about 10. The symbiotic blue-green algae is known for its multicellular cylindrical trichomes that consist of an open left-hand helix, and it undergoes binary fission for reproduction. Spirulina will adapt to light intensity, forming a straight rod structure or its characteristic spiral structure, which allows it to increase or decrease the concentration of light that it receives to perform photosynthesis and cell reproduction. These two structures are compared in the experiment by looking at how strictly coiled spirulina or a mix of both coiled and straight differ in their oxygen production and cultivation responses under the different levels of light intensity. Also, as a cyanobacterium, it is one of the very few groups of organisms that can convert inert atmospheric nitrogen into an organic form, such as nitrate or ammonia. It is able to photosynthetically convert nitrogen and carbon dioxide while producing oxygen and organic compounds, which means that the metabolic waste in the cabin produced by the crew, like exhaled carbon dioxide, can ultimately be recycled by spirulina and converted into useful oxygen. We will now discuss the materials and methods of the experiment, starting with the control culture. These cultures were kept in separate fish tanks, and the mixed culture consisted of a 50-50 ratio of coiled and straight spirulina, and the coiled culture consisted of only coiled spirulina. Two plexiglass covers were used to create a barrier for the algae so that unwanted contaminants were kept out, and each tank also had an air pump at the bottom to keep the spirulina unsettled. The original spirulina cultures were maintained in alkaline conditions with a pH of 10 at 30 degrees Celsius, and they were also given 50 milliliters of Zaruk's nutrient media daily, which you can see the ingredients for on the right side of the slide. Sodium bicarbonate powder was also added as needed to maintain the optimum pH of 10, and deionized water was added to a fill line when the cultures reached a thick green color and just a point of density that prevented light penetration. And then additionally, a white light intensity of 24 micromoles per meter squared per second was kept constant on both tanks of algae throughout the experiments, and the amount of nutrient media added to each culture was also dependent on the culture's growth. So if there was a lower cell count, then more media would be added at a more consistent rate, and then obviously if they were high, then that would decrease. To keep track of the cell concentrations, the culture cell counts were taken every other day and recorded. The cell counts were replicated for each container 3 times from each pulled sample, and then they were averaged. So this average was then multiplied by 10,000 and divided by 4 to calculate the estimated total cell count for each experiment container. For the light experiments, there were 2 incubation chambers that were used to grow the spirulina cultures under the low light intensity at 3 micromoles per meter squared per second and the high light intensity at 8 micromoles per meter squared per second. And once the cultures were placed in the incubators, the doors of the incubators were closed so that only the light they received were strictly from the red light. And then the cultures remained under these red lights for 72 hours, and measurements occurred outside of the incubator at each 24-hour mark. The 4 oxygen monitoring containers were built using plastic containers and 3 collection tubes. So the pictures on the right display the structure of the containers with the 3 tubes I just described. The oxygen production was measured, like I said, every 24 hours by recording the amount of oxygen gas produced in the 50 milliliter and the 15 milliliter tubes. So after the oxygen was recorded, the containers were squeezed to release the oxygen and refill the tubes with algae so that oxygen production could be recorded for the next 24-hour period without the oxygen from the previous 24 hours interfering. The culture cell counts were also taken before starting the experiment and then after every 24-hour period. For the last part of the materials and methods, we're going to discuss the statistical tests that I did. These tests were performed to see if the different light intensities affected the cell concentration and oxygen production in the spirulina. So the null hypothesis assumed that there is not a significant difference between the tested groups, and so to determine if the null hypothesis could be accepted or rejected, multiple statistical tests were performed in RStudio. The data that was used for the statistical tests were the recorded results over each 24-hour period of the cell concentration, oxygen production, and oxygen production per cell. For the cell concentration statistical results, the assumption of the one-way ANOVA were met for the high and low light intensity cell concentrations. So this meant that the p-values were greater than 0.05 for the Shapiro-Wilk normality test and the Bartlett test of homogeneity of variances test. So a one-way ANOVA was run, and it gave a p-value of 0.183, indicating that the null hypothesis could not be rejected and that there was not a statistically significant difference between the high and low light intensities. So this just meant that it could be assumed that any observed differences within the cell concentrations was potentially a result of sampling or experimental error. Here you will see a graph of the average cell concentrations for both the high and low light intensities for the initial cultures and for each 24-hour period, which are labeled day 1, day 2, and day 3. Ultimately, although the differences in the cell concentrations were recorded, the statistical analysis indicated that there were not any significant differences among the groups that were valid. One thing to note is that the cell concentration did fluctuate more than what was anticipated, and there was not necessarily a steady increase throughout the experiment. This could be due to the fact that the original culture cell concentration did not remain constant, and the health of the culture varied at different points throughout the experiment. These graphs show the cell concentrations for each individual experiment for the mixed and coiled cultures at the high and low light intensities. The highest total cell concentration was found to be 225,000 cell per milliliter during experiment 3 for the mixed culture on day 3 at the high light intensity. Once again, based on these statistical test results, the data for the cell concentrations of all 4 experiments did not have a significant difference between the high and low light intensities. The assumptions of the one-way ANOVA were not met for the high and low light intensity oxygen production because the Shapiro-Wilk normality test and the Bartlett test of homogeneity of variances test gave p-values that were less than 0.05. So this meant that a one-way ANOVA could not be conducted, and a non-parametric Kruskal-Wallis rank sum test was run instead to give a p-value less than 0.05. So this p-value indicated that the null hypothesis could be rejected and that there was a statistically significant difference in the data. So a Kruskal-Wallis MC test was also run to determine that the high and low groups were significantly different in the oxygen production. This bar graph demonstrates the averages in oxygen production for the mixed and coil cultures at the high and low light intensities for each 24-hour period once again. The key thing to note from this data is that the mixed culture produced the highest average of oxygen production, which could be a result of the uneven starting cell concentration for the cultures. And the other thing to note is that the 8 micromoles per meter squared per second produced the most oxygen for both cultures. These graphs, once again, are showing the individual oxygen production for all 4 experiments. Similar to the graph on the previous slide, we see the oxygen production for the mixed and coiled cultures at the high and low light intensities for the 3 24-hour periods. During the statistical analysis, as I mentioned earlier, the oxygen production was found to have significant difference between the light intensities. And so in each of these graphs, you will see, except experiment 1 mixed, that the high light intensity produced more oxygen than the low light intensity, which indicated that the algae did perform better under a higher red light intensity than the low. Similar to the oxygen produced, the assumptions of ANOVA were not met for the high and low light intensity oxygen production per cell. Once again, p-values were less than 0.05 and a one-way ANOVA could not be run, and instead the non-parametric Kruskal-Wallis rank sum test was run to give a p-value less than 0.05. This p-value indicated that the null hypothesis could be rejected, and the Kruskal-Wallis MC test was then run to determine that the high and low groups were significantly different in the oxygen production per cell. By looking at the oxygen produced per cell, this allowed me to look at the data with less of a skew because it minimized the starting cell concentration's effects on the oxygen production values. So the high light intensity at 8 micromoles per meter squared per second produced more oxygen per cell on average than the low light intensity for both the mixed and coil cultures when comparing them. And then when comparing the mixed to coiled, the coil culture produced more oxygen per cell on average for both light intensities. Once again, these graphs show oxygen production per cell for each individual experiment for the mixed and coil cultures. We will see that the coil culture produced more oxygen per cell overall at high light intensity, and the highest amount measured of oxygen per cell produced was 9.76 times 10 to the negative 3 centimeters cubed per cell. This graph shows the results of white light intensity for oxygen production per cell during a previous experiment. These results were used to compare the data of the red light intensities for oxygen production per cell. So when considering previous experiments with greater light intensities, the high white light intensity of 25 micromoles per meter squared per second presented the highest oxygen produced per cell. In comparison, a coiled culture after 24 hours at 8 micromoles per meter squared per second produced on half of the 25 light intensity. So despite the 25 white light intensity producing double the oxygen per cell on average, the red light intensity at 8 micromoles per meter squared per second still produced a 24-hour period total of 9.28 times 10 to the negative 3 centimeters cubed per cell in experiment 4, which is greater than any total oxygen production per cell in the white light intensity experiments. So this suggests that with further experimentation, with possibly slightly higher red light intensities, the oxygen production could match the production of white light. When considering future experiments, it is important that the starting control cultures are at a 50-50 ratio so that there's less of a chance for the data to be skewed, and more accurate results may have also been detected had there been more statistical power. And of course, multiple replications of the results are always desired. The results of this experiment suggest that spirulina grown in red light intensities have the potential to produce oxygen at moderately sufficient amounts and potentially greater amounts than white light intensities. Space travel could ultimately benefit from the use of these lower light intensities because the red light intensities, like 8 micromoles per meter squared per second, use less valuable energy when compared to the high white light intensities, like 25. The coiled structure of spirulina consistently produced more oxygen than the mixed culture, so that also should be considered when moving forward. And although there is a lack of understanding as to why, further experimentation could provide more reasoning behind the coiled structure's photosynthetic benefits. With that, that concludes my presentation. Here are my references that I used during my research and my thesis. And once again, thank you for your time and interest in my presentation. This was a very condensed version of my research, and I focused on the main highlights of my thesis. So if you have any questions regarding my research or want to know more, please feel free to reach out or email me. And other than that, I hope you have a great rest of Scholars Day. Thank you.